I know you're a pro, and you know that the integral of a rate is almost always something meaningful. And what we're going to do today is we're going to take that concept and we're going to apply it to a very specific situation. Namely, the integral of f prime of x is something specifically meaningful. Before we get to that, though, I want to just do a quick example of this so that our brains are all on the same page. And this example is going to be very, very simplified. It's raining at a rate of 2.3 centimeters per hour from 3 o'clock to 8 o'clock. How much rain fell in total during that time? Well, I know the rate at which rain is falling, and the integral of a rate is almost always something meaningful, so I integrate the rate at which the rain was falling. Now be careful, it fell for a 5-hour period from 3 o'clock to 8 o'clock. I might be tempted to put a 3 here and an 8 here, but that's not the way it works. During that 5-hour interval, this is like time 0, this is like time 5, so the time goes for 5 hours from 0 to 5. All right, antiderivative, plug in the limits of integration, and now I know how much rain fell because the integral of a rate is almost always something meaningful. Now, of course, back in the elementary days, when you didn't need any integration, you could have just said, hey, if it's falling at a rate of 2.3 centimeters per hour for 5 hours, 2.3 centimeters per hour times 5 hours gets 11.5 centimeters. Same answer. I didn't need integration, did I? Well, of course, the reason we have integration is what happens if someday you run across a case where the rate that you're integrating is much more complicated than that one. In this case, you can't rely on your friend multiplication. You end up doing some real integration, and that's why we're learning this. The integral of a rate is almost always something meaningful, but now we want to apply it to the specific case of the integral of f prime. So here I've put together a simple example. We're integrating from 2 to 6 along the x-axis. The derivative f prime of x, we don't even know what function f of x looks like. But what we're going to get here in this specific case, when you integrate a derivative, in this case a y prime or f prime, you're going to get the change in y value of the original function. F prime of x really is a rate. It's a rate of change, and they've told you that since Algebra 1. Slope is a rate of change. So when I integrate a derivative, I'm integrating a slope, which means I'm integrating a rate of change. And what it means is the ultimate change in y value of your original function. I'm going to show you this, but instead of using some symbolism that doesn't necessarily mean something, we're going to take an actual problem and just show you how that works. So here I have f prime of x being replaced with a very simple derivative of 3 halves. So what I'm knowing here is f prime of x equals 3 halves. And if I integrate that, integration by hand, I end up with a value of 6, which means some function f of x increased in y value by 6 units as we traveled from x equals 2 to x equals 6. Well, in a case like this, when I have a derivative that's as simple as that, I might be able to reason out what the original function f of x was. In fact, let's take a look here. I made up a function that very easily could have the derivative of 3 halves. So f of x, 3 halves x minus 5, I just made up the minus 5. Here's a graph of that function. This derivative would be 3 halves. So if I integrate from x equals 2 to x equals 6, and I got a value of 6, let's take a look at what that means in graphical form. There's x equals 2, there's x equals 6, and as I travel along my graph, my y value went from -2 all the way up to 4. So as I went along the x-axis from 2 to 6, my y value went from negative 2 up to 4. That's a net change of 6 units along the y-axis. That's why that integral was 6. So that's just supporting in a really easy way this fact that you probably need to memorize. If I integrate a derivative, I get a change in y value of the original function. And you can use this in a much more complicated situation. So here's a case where I have a derivative, e to the cosine of 2x. Well, I don't know that I could find out the antiderivative of that right now, but if for some reason I cared about the change in y value of that function as I went from 1 to 3 on the x-axis, I can simply integrate that. In this case, I would go right to my calculator. Thank you, calculator. And I get a 1.870. That means my function f of x, which I don't even know what it looks like, increased by 1.87 units as I traveled along. Or the difference in their y values is 1.87 units, or f of 3 is bigger than f of 1. These are all 3 different ways to say the conclusion that we got, but they're all based upon the fact that if I integrate a derivative, I get the change in y value of my original function. And it's important to know that we could have a negative result of our integral. If this ended up being negative 4, that would just mean my mystery function f of x decreased by 4 units as it went along that interval along the x-axis. This is important information to put into your brain, and the AP is not shy about throwing a few of those questions on the AP test. See ya!